then you split the middle. Very nice. If you have an even number, you just go 13, 13, and you average the two in the middle. And it won't actually be one of the data points. It'll be directly between them. That actually happened last class this morning. Exactly 16 data points. So we had to split all 3 of these. Perfect, perfect. So let's go in 14 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's one of those guys. Also, going in this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'll be damned. And it has to, right? It has to do that. I mean, that's the beauty of symmetry. Oh, wait. Yeah, 13. There's your median.
Thank you.
There's your median. Let's find the quartiles in the same way. Now let's think about this. You think to yourself, wait a minute, how could you find them in the same way?
Half of 13.
Good. You have to go to basically the 6.5. Well, actually, no. The 6.5 spot, it would be the 7th spot. Because to take your bottom 13. Now this is where software sometimes disagrees with pure logic. And it depends on what, it depends on what formula it's using. So since we have 27, there is 1 in the middle. So I'm going to use the bottom 13 and find the middle of that 13. Well, think about 13. Break it in half, but have 1 in the middle. 6 and 6. So it's going to be the 7th spot. You guys buy that? So the 7th spot. So essentially, you're finding a median again, aren't you? But it's a median of the half created by the median. It's kind of like a strange way of saying it. Yeah, exactly. It's the median of the lower half, right? So let's come in. What do we say? 7? 1, 2, 3, 4, 5, 6. Boom. There's your lower quartile. Right there. It's the median of your lower half. Now what's cool about that number? What's cool about that number is we already know the median divides the lower half of the data from the upper half of the data. What does Q1 divide? The lower, go ahead, Corey.
Half of it.
Good, the lower half of a half, otherwise known as a quarter. Very nice. The lower quarter from the upper 3 quarters. Did everybody catch that? That was half of a half. You took the half and you cut it in half again. So now, 25% of all of your data points are below this guy. What percent are between Q1 and the median?
25%.
Another 25%. Beautiful. And then let's find Q3 in the same way. Let's use that 7 again, because it's still going to be 7, isn't it? Because you have 13 above. So we'll go 7 in from the end. We got 1, 2, 3, 4, 5, 6, 7. Boom, right there. There he is. Here's Q3, which agrees pretty nicely with that right there, 16. So there's Q3, which means now we know that 25% of our data are above Q3. And the last 25% are between Q3 and the median. That's what you're talking about. When you have this Q3, Q1, Q2, all these wonderful quartiles, all you're doing is you're setting up fence posts that are dividing percentages up. That's all. You're dividing your numbers into percent chunks. Why is it important? Why would you care? This is a great question. Is this just a torture method? Is this something to torture you guys? But Lucas, why would you care about this?
It's easier to explain where data's falling. Right?
Exactly.
Oh, well, that's going to be in the third.
No, dude, you got it. That's
yeah,
exactly what it
It's
is.
Use it as
an easy way to see your standard deviation.
Yes!
You know that's 50, and it's supposed to be within 63, so I just go out a limit so that the main population is going to fall right there in the center.
Listen to that. That was wonderfully said. What Athena just said, it's kind of like, it was like tagged off what Lucas said. You know how we have that wonderful empirical rule? 68%, 2/3 of your data fall within a standard deviation, 95 within 2. What's the big if with the empirical rule? If it's bell-shaped, Kelsey. What if it's not? Well, then you can't use it. But with shoot. But what you can do is you can always create this kind of a setup and say, well, look, half of the data we have is between 9 and 16. And that'll always be the case regardless of the shape of the data. Regardless of the shape of the data. Half of it's going to be between 9 and 16. This works for bell-shaped data too, but it works more generally for all data. And that's pretty slick. It gives you a guaranteed behavior mechanism for your data. Fantastic. Now, although it is wonderful, and I agree it's wonderful, it's also a bit of a headache to look at like that. And if you have large data sets, it's even worse. So, what I'm going to recommend we do is create one new graph today, and then we'll show you how to get it on your TI. That's the most fun, is get your TI to generate it for you. And then we'll play with it again on Monday. I want to kind of get this data set done today, so we can start with a fresh data set on Monday, and then bring all these ideas back. There's a really cool graphical display that uses these guys called a box and whisker diagram. And basically, essentially what it does is it's a neater version of what I just did in blue and green on that dot plot. So bear with me here. Where Q1 and Q3 are, above that, draw a couple like vertical lines, and then make a box out of those vertical lines. Athena, what's in that box? You just said it beautifully. You just said it beautifully. I don't mean to pick on you.
Pretty much your 68% of the average.
You can't guarantee 68, but you can guarantee 50% of your data is within that
The
box.
majority of my people are.
Good. Well, it depends on, and this is interesting. I'm really glad you brought that up. It depends on how you define majority.
Well, I guess you're right.
Half of your data.
Okay, well, half of my data, because
Awesome.
are the
Center.
And the reason, say that again.
Center half.
The center 50%, the middle 50% of your data live in that box. So now what you're getting is you're getting another way to measure typical. The middle 50%, not the extreme low, not the extreme high, the middle 50%. You're getting one more way of talking about a typical behavior point of data. So the middle half of our class, between 9 and 16, those were the, if you will, quote unquote, typical. So we're getting some intersection between absolute and relative, which is cool. That's what it should be. You should be talking about your data in a number of different ways. But that's just the middle 50%. And speaking of which, one last little line that helps in the box is where the median is. It's very nice to see your median line drawn in there too, because, well, we'll come back to that. We'll come back to why that's important in a minute. Some folks also add the average to a box and whisker with some other symbol. I tend not to, only because I like keeping it separated from relative to absolute, but you can. If you see like a triangle or something on a box plot, that's usually what it means. How about the whiskers? What are the whiskers? Where do you think they go?
To the max and the min.
Exactly, Eric. They go out to the other extremes, the max and the min. So our min was 3, so we're going to put your one whisker here, draw it in, and you are. And then all the way up to 33, and that guy right there, it's a beautiful, it's a wonderful, wonderful, wonderful graphical display, and it's a great way to unplug your projector. It's a great way to do comparisons, which we'll get to on Monday. It's called a box and whisker, or sometimes just called a box plot. It's one of my favorite graphical displays in statistics. One of my favorites, because it's so simple to make. All it takes, as opposed to a bunch of raw data, is 5 simple numbers, the min, the max, and the 3 quartiles. What else can you get from that box plot besides just those quartiles and the min and the max? What else can you tell a little bit? 50%, I love that. I love that already. You guys nailed that one.
I was thinking the majority of your average people are going to fall. That's
Absolutely. You've defined average as center, and I love that idea.
the majority of the.
Right? So you've got the low 25% fall between here and here.
Your outliers.
Nice. And more on those. This actually helps us decide if we have any outliers. A mathematical way. Right now, we've been using that word a lot over the past couple weeks, right? We've been saying outlier, but when we talk about outlier, sometimes we just talk about the largest and smallest. The word outlier actually has a pretty, it's got a more specific abstract meaning. And it's unusually small or unusually large or unusually different. Is the biggest data point actually unusually large, or is it just the largest? Is a 6'4" dude like surprisingly tall or just tall?
Can you tell by the length of the whiskers?
Yes, friend. Let's get it out on Monday. We have some more data if you don't mind. Yeah, the length of the whisker when compared to the box, that's what really does it. When we do a relative, and I'm not saying this is absolute. This is humans creating these rules. But that's one way of measuring it. Go ahead, Athena.
It's almost double the average, the last one.
Good. But here's the deal, though. Here's the deal. Okay, Lucas. Yes. This is your middle 50%. One way of measuring unusualness is take that, increase it by 50%, and then stack that right here.
And it's still outside.
If it's outside that, it's called a mild outlier.
Okay.
If you take that and increase it by 3, and anything's outside that, it's called an extreme outlier. So technically speaking, the box is the measurement, so to speak.
Sweet.
That's one way of measuring outliers. And like I said, I don't want to do this just verbally. I want to write this stuff down on. And measuring this is important. And for some reason, your book doesn't talk about it at all. So I created a section on it. That'll be the section after this one where we actually sit down and measure outliers in different ways. And there's at least 3 or 4 different ways that are used pretty frequently to identify them. Speaking of those whiskers, look at the one on the right. It's longer. Is this what you said, Lucas? The one on the right is so much longer than the one on the left? Say that again.
Yeah, that's what I was-
It shows skew in the data. Or at least, even if it's not skew, what does it show? Use a more general term that we've used already. I love the fact that you're saying skew. What's an analogous term for skew that's more general? I like that. Imbalance, good. I was thinking variability. But skew, imbalance, and variability, they all mean the same thing, right? They mean falling out of symmetry, basically.
There's what it does is it displays more variability with a whisker is larger, let's say, on either side, and there's less variability on the one that shows.
Yes, and even the box shows that, right? Look at the box. Which side of the box shows more variability? It's not a marked amount like the whiskers are, but which side of the box shows more variability? The left side is wider. The wider the box, the more spread the data are. Oh, spread in data, that's variability, right? So there's so much contained in that box plot. That's why I love them. There's so much wrapped up in there. You get a little bit of center. You get a little bit of skew. You get it all kind of at the same time. And I really wish that the TIs would put the dot plot with the box. We can approximate it closely. We can get a close approximation. I'd like to kind of wrap up with that today with your TIs. One more back to the TI. Kelsey, I love what you said earlier about forgetting the steps. No, it's good. That's why I want to keep going back to it. Same data, grab your TIs. Let me clear a little bit of space here on the front board. We'll leave that one up there. We'll come over here. Yeah, I mean, the box plot and multiple box plots, I like those even more in a lot of ways. Fire these bad boys up. Okay, so we've got our histogram. Yay, us. Looks kind of obscene, actually. Flipping me off.
What?
Looks like it's flipping you off.
It kind of is.
That's great.
Or the outliers. On average, flipping you off. So, go back to your stat plot menu. Second y equals. Second y equals. Leave plot 1 there. I want to leave him on. Turn plot 2 on, too. So select him, press on for enter. Exactly. And there's 2 of them. There's this one and this one. Don't worry about him right now. We'll play with him more. I want to revisit that idea that Lucas was talking about the length of the whisker and how it governs the outliers. We'll get back to that on Monday. When you get the histogram, scroll through until you get to this guy right here. That's your box plot. Yeah. And you have to scroll to it by arrowing to the right until you get on top and then press enter. And then just make sure X list is on L1 and your frequency list is still set on 1. Once you've got it set up, just press graph. And there it is, right with your histogram. Right with your histogram. Oh, Eric, go ahead.
I got like a weird,
Press just Y equals, my friend. You got anything in there?
Yeah.
Clear it out. Also, is your guy's box plot sitting right on top of the bar like this?
Yeah.
Of course, you can mess with that. You can go into the window button, and you can adjust your Y max to say 20 this time instead of 15. Change the scaling if you want to. Now we got a box plot sitting on top of the histogram, and you can do the same thing we did earlier, where you can hit trace, which is the other button up there on the top row. Now right now you're still on your histogram. To get up to the box plot, just press up. And then you can scroll through and actually get your values. 33, and it labels them for you down there. This kind of makes up for not having the scale, although I still don't like it. I'd much rather have the scale on there. This is kind of slick. The TI is a little bit of a pisser too. I would love to make the histogram a box plot. It is. Like it's just some limitations that really drive me nuts. So if you press the window button again, in order to make the histogram a dot plot, what would that have to be?
1?
1. It would have to be 1, wouldn't it? Each bar would have to be 1 wide. The problem with that is, the way the TI is set up, it won't let you do that. And here's why. Here's why again. I think anyway, so I think it is. Change it to 2, which is about the smallest you can get to, ish. There. That's close. That's close. I think the reason is, when you press trace, you'll see why. The first bar has to start at a value and go up to a value, and you can't be equal and less than the same value. I think that's the issue. I'm guessing. I don't know if it's actually right or not. So anyway, this is as close as we can get to a dot plot. But you still get the idea, don't you? You still even set it 2. you still get the idea. Let me bump this down to 10. You still get the idea because you get this cluster right here, and the cluster corresponds to little tiny regions left to right, and then you get this crazy variance over here, which corresponds to that y right there. So what's cool is the more we do this, the more you'll get good at looking at that and envisioning that, and looking at that and envisioning that. And that's why we'll do this just about every day that we can. Okay, Noble? All right, no homework for tonight. Do the take-home part of your exam, yes? Yes, it's got an Excel component. If you get stuck, email it to me. Yes, sir. And I'll get you your other exam back on Monday, the graded part of your exam back on Monday.
Hey, Sean.
Sir?
How do I get this?
Oh, yes, Michael, 89. Let's figure that out. Let me turn the camera off, too.
Excuse me, sir.
You are not turned off yet.